46,000 messages hit Discord servers every single second. Picture a diner at rush hour, orders flying in faster than any cook can file them alphabetically. Most databases work like a filing cabinet. Find the exact folder, insert the paper. Discord needed something different, a ticket rail where every order just clips onto the end. That one idea changed everything. Storing a chat message sounds trivial. Users, messages, channels, store them, done. But messages are write-heavy, time-ordered, append-only, and wildly uneven. A RAID server firing 1,000,000 writes a minute versus a quiet DM. Discord's first database couldn't handle that mismatch. It was about to learn the hard way. In 2015, Discord launched on MongoDB. Indexes lived in RAM. Fast, cheap, simple. As servers grew, indexes outgrew memory. MongoDB started swapping to disk. Latency jumped from 1 millisecond to over 100, with zero warning. By 2017, outages were routine. The filing cabinet was overflowing. Here's why. MongoDB, Postgres, MySQL all use B trees. Like a filing cabinet, every write means finding the exact alphabetical slot, seeking across disk. That seek costs 5 to 10 milliseconds every time. At 46,000 writes a second, that filing cabinet collapses. Discord needed a database built like a ticket rail, not a cabinet. Here's what nobody tells you. Making writes fast makes reads harder. A ticket rail has no search function. You scan from the newest ticket backward. Cassandra's LSM trees trade instant random access for raw write speed, then claw back read performance with tricks like Bloom filters. That trade-off is the whole game. Remember the ticket rail? Here's exactly how it works inside Cassandra. A message lands, gets appended to a commit log on disk. Sequential, instant. Then it's mirrored into an in-memory mem table. The client gets a success response in under a millisecond. No searching, no random seeks, just clip and go. Eventually the mem table fills, 64 to 256 megabytes, and flushes to disk as an SS table, a sorted permanent file. Old SS tables quietly merge in the background, clearing duplicates and deletions. It's the busboy clearing the rail while the kitchen keeps firing orders, non-stop in the background. Cassandra doesn't run on one server. It's a ring of commodity machines. Every partition replicates onto 3 nodes, so one server dying doesn't lose a single message. Discord's ticket rail isn't one counter. It's dozens, spread across a cluster, each holding a slice of the traffic. The real decision wasn't picking Cassandra, it was this schema. Partition key, channel ID, clustering key, message ID, sorted descending. That combination decides where every message lives and in what order it comes back. Get this wrong, and no database engine saves you. The partition key, channel ID, tells Cassandra exactly which nodes hold that channel's messages. No scatter-gather, no guessing, just a direct hash lookup straight to the right rail. Every channel gets its own dedicated ticket line, spread across the cluster by design. Inside that channel's rail, messages sort by message ID, newest first. Scrolling up in Discord is just a sequential scan backward through the rail. No index lookups, no random reads, just grab the next 50 tickets in line, a query that takes microseconds on SSD. Discord's biggest public servers push a single channel partition past hundreds of millions of rows. Cassandra calls this a wide row, and it's exactly the shape it was built for. One rail, endlessly long, still served in microseconds. Every message needs a unique ID. The obvious move, auto-increment, needs one central counter. One counter means one bottleneck. At 46,000 writes a second across hundreds of machines, that counter becomes the whole system's ceiling. Discord needed IDs generated everywhere with zero coordination. Twitter's 2010 fix, Snowflake IDs. 41 bits of timestamp, 10 bits for the worker machine, 12 bits for a per millisecond counter. Any server mints IDs alone, up to 4 million per millisecond, cluster-wide, with zero central lock. Because the timestamp sits in the top bits, Snowflake IDs sort numerically by creation time, automatically. Message ID is chronological order. Discord's clustering key isn't a coincidence. It's the Snowflake ID doing double duty as unique key and built-in sort order. When you open a channel, Discord checks Redis first, a cache holding the last 50 to 100 messages. Most of the time, that's a hit. Latency, about 1 millisecond. The ticket rail never even gets touched. This handles the overwhelming majority of reads. Scroll back far enough, Redis misses. Now the app queries Cassandra directly, a cursor-based scan through the sorted rail. Slower than Redis, still fast, because clustering keys keep everything pre-sorted on disk. 2 paths, 1 system, tuned for how people actually chat. Now the danger. Picture a massive announcement channel during a live event, millions hammering the same partition key at once. All that traffic slams into the same 3 nodes. One overloaded rail can't serve millions of orders at once. This can take a whole cluster down. The fix: bucket sharding. Instead of one partition per channel forever, Discord splits it by time window, 1 rail per hour during huge events. Traffic spreads across many partitions instead of choking one. It's opening more ticket counters the moment the line gets too long. With replication factor 3, Discord picks per query how many replicas must agree. Quorum needs 2 of 3 to confirm, a balance of speed and safety. One is faster but riskier. This tunability is the interview answer that separates candidates who've read the docs from candidates who've shipped it. By 2023, 4 billion messages a day, 46,000 writes a second sustained, tripling during major events. Trillions of messages stored total. Numbers that would flatten a filing cabinet database. Numbers a ticket rail architecture eats for breakfast. 6 years running Cassandra, and Discord hit a new wall. Not data, not capacity. Cassandra runs on Java, and Java's garbage collector randomly freezes every thread to clean memory. At Discord's scale, those pauses showed up as ugly latency spikes nobody could schedule around. The fix wasn't a new data model, it was a new engine. ScyllaDB rebuilds Cassandra's exact architecture in C++ with 0 garbage collector. Same schema, same partition keys, same ticket rail logic, just no random freezes. Discord swapped databases without touching a single line of application code. The result: P99 read latency dropped from up to 125 milliseconds to under 15. Same schema, same Snowflake IDs, same ticket rail, just a faster kitchen behind it, an 8x improvement in tail latency with 0 code changes on the application side. The full journey: MongoDB in 2015, overwhelmed by 2017. Cassandra took over, scaling Discord into the billions. By 2023, ScyllaDB pushed it into the trillions. Same core idea the whole time: sequential writes beat random ones at every single scale. In your next system design interview, say exactly this: for write-heavy, time-ordered data, I'd reach for an LSM tree store like Cassandra, partition by entity, cluster by a sortable ID, and watch for hot partitions. That one sentence signals you've actually thought about this before. Discord never went back to filing cabinets. Every message still clips onto a ticket rail, spread across thousands of nodes, sorted by time, ready in microseconds. Remember that image, and you'll never forget how write-heavy systems scale. Subscribe for the next deep dive.